Dear students, in the last class, we have seen that the problem of estimation consists of point estimation and interval estimation. In the case of point estimation, we suggest a single value for the parameter. In the case of interval estimation, we suggest a range within which the parameter will lie. The range is constructed by taking 2 or 3 standard deviations of the estimator. Now today, we explain the construction of confidence intervals. We start with how to construct a confidence interval for arithmetic mean first, because this concept will be familiar to most of the students. Then we will consider how to construct confidence intervals for OLS estimators, confidence interval for the regression coefficients beta 1 and beta 2. So first we explain the construction of confidence interval for the parameter mu using estimator x bar, arithmetic mean. Now we know that if x is normal, the mu and sigma square, x bar is also normal with the mu and sigma square by n. So that z is equal to x bar minus mu by sigma by root n. It is standard normal with the 0, 1. Now, if we know the standard error of x bar, that is, if sigma is known, we can use z for constructing confidence intervals. So first we assume that sigma is known, and as x bar is normally distributed, we use normal distribution for constructing confidence interval. Now, let us see how the confidence interval is constructed for the parameter mu. We know that the probability that minus z alpha by 2 less than or equal to or less than z alpha by 2 is equal to 1 minus alpha. It is a statement about the probability that z lie between two intervals is equal to 1 minus alpha. Now suppose that we fix alpha as equal to 0.05 or 5%. Multiplying this with 100. Then it becomes 1 minus 0.05 is equal to 0.95 or 95%. That is, 95% of z lie between these two intervals. If alpha is fixed at 5%, then this becomes minus 1.96 and this becomes 1.96 plus. We know that 95% or 0.95 or 95% of z lie between these two values. Now this minus z alpha by 2 and z alpha by 2 are known as the critical values, and z in the middle is the empirical z, that is the z obtained from the sample. So z in the middle is this z, that is x bar minus mu by sigma by root n, and Z alpha by 2 is Z for alpha by 2 level of significance. Alpha by 2 level of significance known as critical Z values. Critical Z values. So substituting for Z, probability that minus Z alpha by 2 less than x bar minus mu by sigma by root n less than Z alpha by 2 is equal to 1 minus alpha. Remember this, we are considering the sampling distribution of x bar and the Z derived from this sampling distribution to construct a confidence interval for the parameter mu. The parameter mu. This can be written as probability that minus Z alpha by 2 into sigma by root n less than x bar minus mu less than Z alpha by 2 into sigma by root n is equal to 1 minus alpha. Assuming that all the terms are multiplied by sigma by root n. Sigma by root n. Then this is same as probability that minus Z alpha by 2 sigma by root n minus x bar, and x bar is subtracted from all the terms, minus mu less than Z alpha by 2 sigma by root n minus x bar is equal to 1 minus alpha. X bar is subtracted from all the terms. Now, assuming that we multiply all the terms with a plus, this becomes probability that x bar plus Z alpha by 2 sigma by root n. Then when we multiply throughout with the minus, the inequality reverses. Greater than mu, greater than x bar plus minus x become plus x bar minus Z alpha by 2 sigma by root n equal to 1 minus alpha. Equal to 1 minus alpha. X bar plus Z alpha by 2 sigma by root n greater than x bar minus Z alpha by 2. Now, I write this first. Then we will get a probability x bar minus Z alpha by 2 sigma by root n less than mu less than x bar plus Z alpha by 2 sigma by root n is equal to 1 minus alpha. Is equal to 1 minus alpha. So, the 100 into 1 minus alpha percent, 100 into 1 minus alpha percent confidence interval for mu is equal to x bar plus or minus Z alpha by 2 sigma by root n. Z alpha by 2 sigma by root n. If alpha is 0.05, we can write this as mu is equal to x bar plus or minus 1.96 sigma by root n. Sigma by root n. X bar plus or minus 1.96 sigma by root n if alpha is 0.05 or 5%. Now this is Z alpha by 2, confidence interval for the parameter mu, or this is the 95% confidence interval for the parameter mu if alpha is fixed at 5%. And this is how we derive the confidence interval for any parameter. So first multiply by sigma by root n, then an x bar is subtracted, multiply throughout with a minus, This is only a rearrangement. This will give a 100 into 1 minus alpha percent confidence interval, not for the estimator, but for the parameter. Always remember that. We are constructing confidence intervals for parameters, not for estimators. Now, this can be generalized. This can be generalized for any estimator. And consider this. This is 1.96 into sigma by root n. Sigma by root n is the standard error of the estimator. And sigma by root n is nothing but the standard error of the distribution of x bar, and x bar is assumed to be normally distributed. X bar is assumed to be normally distributed. Now, as we have discussed in the last class, if x bar is given, x bar is calculated from the sample, and if sigma is also known to us, but in most cases sigma will be unknown. Anyway, if known to us, n is the sample size, we know that. We can use Z distribution for construction of confidence intervals. But in empirical applications, in applied research, this sigma will be unknown. If a sigma is unknown, we cannot use Z as the test statistics. If sigma is unknown, and if sigma is replaced by its unbiased estimator S or sigma hat, then we have another distribution. The distribution is the T distribution. So, if we assume that sigma is unknown, we use T distribution to construct confidence interval for population parameter mu using the sample statistics x bar. Now let us see how to construct confidence interval using T distribution rather than Z. Now, as we have discussed in a previous class, T is equal to x bar minus mu by S by root n. This quantity follows T distribution with n minus 1 degrees of freedom. As I told you, whenever sigma is replaced by its unbiased estimator S, the distribution becomes T with the degrees of freedom equal to n minus 1. N minus 1. Let us see how it is. As we have discussed in a previous class, if Z1 is standard normal, we know that x bar minus mu by sigma by root n is normal with 0 and 1, standard normal, and Z2 chi-square with k degree of freedom, and in this case n minus 1 degrees of freedom, and we define Z2 as n minus 1 into s square by sigma square, which was written as sigma x minus x bar square by sigma square. This quantity follows chi-square with n minus 1 degrees of freedom. And Z2 is distributed independently of Z1. Then Z1 by root of Z2 divided by the degrees of freedom follows T distribution with the n minus 1 degrees of freedom. Substituting this and also this in the definition of T, you will get the T distribution. So Z1 x bar minus mu into root n by sigma divided by root of sigma x minus x bar square by sigma square divided by n minus 1 into 1 by n minus 1. This sigma and sigma will cancel. Sigma and sigma will be cancelled, and you will get x bar minus mu by this quantity is then sigma x minus x bar square by this quantity becomes x bar minus mu by then the sigma and sigma root of sigma square will be cancelled. Then in the denominator we have s by root n is written s by root n. That is the T distribution. So let us see how we use the T distribution for constructing confidence interval. Now, again, as we have discussed in the case of Z, we can make a statement like this: probability that minus T alpha by 2 less than T alpha by 2 is 1 minus alpha. If alpha is 0.05 or 5%, if alpha is 5%, this is the 95% confidence interval for T. This T is nothing but the T distribution obtained from the sample, or empirical T. Substituting for T, you will get a probability that minus T alpha by 2 less than x bar minus mu by s by root n less than T alpha by 2 is equal to 1 minus alpha. Now there is a point here. If alpha is fixed at 5%, then from the Z distribution, the critical Z values are minus 1.96 and plus 1.96. 95% of Z lie between these two intervals. This is not true in the case of T distribution. In the case of T distribution, if alpha is fixed at 5%, 95% of T depends on the degrees of freedom. So we have to consider the degrees of freedom also. For example, if our degrees of freedom is 20, then 95% of T lie between 2.036 minus and plus 2.036. So this becomes minus 2.036 plus 2.036. And when the degrees of freedom is different, you have different critical T values. If degrees of freedom is 8, it is 2.3 something. So the critical T values depends on the degrees of freedom or sample size. Now, just as we did in the case of Z, multiply throughout with S by root n, subtract x bar, multiply throughout with a minus, you will get probability that as we have done in the case of Z distribution, probability that x bar minus T alpha by 2 into S by root n less than mu less than x bar plus T by alpha, T alpha by 2 S by root n is equal to 1 minus alpha. 1 minus alpha, or mu is equal to x bar plus or minus T alpha by 2 S by root n. S by root n. As I told you, if degrees of freedom is 20, you can write it as, and alpha is 5%, you can write it as x bar plus or minus. This T alpha by 2 can be written as 2.036 S by root n. For a different degree of freedom, you have a different confidence interval. So this is the confidence interval from the T distribution. And remember this, if you are doing research using your own data, sample data collected by you, or sample data or secondary data obtained from some other agency, sigma will never be known, because if you want to know what is the population variance, the entire population will be known to you. But this will not be available in the real situation. For doing a problem in the classroom, the value of sigma will be assumed, and we can use Z for constructing confidence intervals. But in the case of real world data, we cannot assume the value of sigma. So what we do in the real world is we replace sigma with its unbiased estimator S. And as I told you, whenever the population variance or standard deviation is replaced by its unbiased estimator, Z distribution is converted into T distribution. Then we can use only T distribution for constructing confidence intervals, and as we will see later, for hypothesis testing also. But if the sample size is very large, technically you will get a T value equal to 1.96 only when degrees of freedom is infinity. You will get a T value equal to 1.96 only when degrees of freedom is infinity. For any degrees of freedom, there will be some difference between the critical Z and T values. But if the sample size is very large, you can use Z or T. What I say is, you are using the sample standard deviation, but you can use Z in large samples. As I told you, sigma is never known. So this is how we construct confidence intervals. How we consider confidence interval. If Z is used, then mu is equal to x bar plus or minus Z alpha by 2 sigma by root. Here the difference is S by root n, sigma by root n. Z alpha by 2 replaced by T alpha by 2, which depends on degrees of freedom. If alpha is 5%, here there is only one value. But here it depends on the degrees of freedom also. So the value vary from sample to sample depending on the sample size. And this is how we construct confidence interval for population mean using the estimator arithmetic mean.